A new space race is unfolding in secret laboratories and orbital workshops. This is the inside story of the global race to develop quantum-linked space navigation systems, a competition that will redefine power on Earth and our pathway to the stars. By the end, you will understand exactly how this hidden technology will reshape your future. We will uncover why nations are risking billions and what mysterious quantum advantage makes these systems nearly impossible to hack. How far are we willing to go to secure the ultimate high ground? Albert Einstein's spooky action at a distance is no longer just a thought experiment. It has become a blueprint for the future of travel. The strange connection between entangled particles, where measuring one instantly influences its partner, no matter how far apart they are, holds the key to a navigation system unlike any before. Imagine two perfectly synchronized clocks, one on a satellite and one on your spacecraft. If those clocks were built from entangled particles, their ticks would remain in perfect lockstep forever. By comparing the quantum states of these separated particles, a ship could calculate its exact position without ever listening for a faint signal from Earth. This idea of a universal quantum ruler emerged from theoretical physics and quickly captured the imagination of engineers. They saw a path beyond the vulnerabilities of GPS, which relies on radio waves that can be blocked, mimicked, or drowned out by interference. A quantum positioning system would be inherently secure because any attempt to eavesdrop or jam the quantum link would disturb the delicate entangled state, immediately revealing the intrusion. This fundamental shift from broadcasting signals to comparing quantum states marks the true beginning of a new age, and that is precisely why this obscure scientific principle is now at the heart of a fierce and secretive global race. Think of it as two coins, each spinning in a different galaxy. No matter the distance, the moment one lands heads up, the other flips to heads up in that exact same instant. This is the strange magic of quantum entanglement. It is a profound, instantaneous link between two particles, a connection that defies our everyday understanding of space and time. For the engineers building our future in space, this is not magic. It is a tool. If you place one of a pair of entangled photons on a satellite and its partner on your spacecraft, any change or measurement you make to one is instantly known to the other. This creates a shared, secret reference frame, a private language spoken only between the 2 points. The system does not need to broadcast a signal that can be faked or jammed. It simply consults this unbreakable quantum link. This provides two critical advantages: perfectly secure communication and timing so precise it is almost beyond comprehension. And timing is the invisible foundation of all navigation. Knowing exactly where you are is a direct function of knowing exactly when you are. This potential to build a navigation system that is fundamentally immune to spoofing and blocking is the very reason this technology is a game changer. It is why nations and corporations are pouring billions into turning this quantum principle into a practical tool for securing everything from global shipping lanes to the pathways between planets. The United States is building a quantum compass for its future in space. This is not just another research project. It is a strategic national priority, driven by the urgent need to protect its most vital systems from disruption. The Defense Advanced Research Projects Agency, or DARPA, and NASA are at the forefront, channeling immense resources into programs with names like the atomic clock with enhanced stability. Their goal is a single, powerful concept, PNT independence, that stands for positioning, navigation, and timing. It means creating a system so self-reliant that it never needs to look at the familiar GPS satellites again. The entire modern world, from financial transactions to power grids, runs on the precise time provided by GPS. That makes it a colossal and tempting target. A quantum-based system would sever that vulnerability at its root. To achieve this, American engineers are focused on a seemingly impossible task: building quantum instruments so sensitive they can feel the universe itself. They are shrinking quantum accelerometers and gyroscopes down to a size practical for spaceflight. Think of a gyroscope as a quantum spinning top that never loses its balance. An accelerometer is like a hypersensitive feather that registers the slightest push. Together, they allow a spacecraft to sense every tiny change in its speed and direction entirely on its own, creating a perfect internal map of its journey without ever asking for directions from Earth. This is where the vision becomes hardware. Corporations like Honeywell and Cold Quanta are in high-stakes laboratories, developing devices tough enough to survive the radiation and extreme temperatures of space, yet delicate enough to measure the subtle whispers of quantum states. They are constructing what can only be described as a resilient quantum backbone for the next generation of military and commercial satellites. This aggressive American push is about more than technological pride. It is a clear statement of intent to control the ultimate high ground, ensuring that the pathways of space remain open and secure on their terms. This ambition sends a powerful signal across the globe, one that other nations are already rushing to answer. While the United States builds its quantum compass in high-security labs, another power is making its own bold moves in the open. China has publicly staked its claim to the quantum future, declaring its ambition to lead the world in this new science. The world took notice in 2016 with the launch of a small satellite named Mishus. This was no ordinary spacecraft. It was a quantum pioneer, successfully performing experiments that once seemed like pure fantasy. Mishus demonstrated quantum key distribution between space and Earth, proving it was possible to maintain that fragile, spooky link across the vacuum. It was a watershed moment, a statement of capability that echoed in research centers from Washington to Moscow. This was not a one-off experiment. It is the visible edge of a massive, state-coordinated strategy. China is funneling immense resources into a network of universities, research institutes, and its powerful state-owned aerospace corporations. Their goal is a comprehensive quantum ecosystem. While navigation is a critical piece, their vision extends much further. They are actively building the foundations of a quantum communication network, a system often described as an unhackable internet. This is the dual-use nature of the technology laid bare. The same quantum principles that could guide a civilian cargo ship through a storm can also guide a hypersonic missile with pinpoint accuracy. Chinese researchers openly discuss applications for their most advanced vehicles, from submarines that navigate the ocean depths without revealing their location to missiles that cannot be fooled by electronic warfare. The sheer scale and startling speed of their progress is a direct and deliberate challenge to the long-held technological dominance of the West, cementing their role as a central and formidable actor in this high-stakes contest. A third path is emerging in this global contest, one built not on solitary ambition but on collective strength. The European Union is charting a course defined by deep collaboration across its member states, creating a powerful consortium of minds and resources. While the United States and China pursue their sovereign goals, the European Space Agency is orchestrating a symphony of nations under initiatives like its Moonlight program. This ambitious project aims to weave a net of communication and navigation services around the Moon itself. and quantum sensing is the invisible thread that will make it all possible. This is not a race for a single flag, but a coordinated effort to build shared infrastructure for the entire lunar economy. Behind this grand vision, research consortiums are the true engines. France's space agency CNES, Germany's Aerospace Center DLR, and the United Kingdom's quantum technology hubs are pooling their finest intellects. Their focus is on a breathtaking piece of technology known as a cold atom interferometer. Picture this device as a trap that uses intricate webs of laser light to catch atoms and slow them down, chilling them to a temperature within a whisper of absolute zero. At this profound cold, atoms behave less like tiny balls and more like gentle, spreading waves. This allows them to become the most sensitive measurement tools imaginable, capable of feeling the subtle tug of the moon's gravity or detecting the faintest twist of a spacecraft. The European strategy extends far beyond simply keeping pace with its rivals. It is about shaping the very fabric of the future quantum economy by establishing the rules that everyone will eventually follow. This cooperative model, though it can move with the deliberate speed of international agreement, holds a unique power. By building systems that are the product of many nations, Europe aims to create technologies that are inherently more robust and, crucially, more universally accepted. This is how Europe intends to leave its distinct and enduring footprint on the final frontier, proving that in the race to redefine navigation, there is profound strength in unity. Yet beyond the grand strategies of nations, a different kind of engine is powering this race. A vibrant and agile ecosystem of private companies is pushing the boundaries of what is possible, often from unassuming offices and workshops. These firms are tackling the fundamental roadblocks that have long held quantum technology back, operating with a speed that can outpace even the most well-funded government program. In Australia, a startup named Q-C-T-R-L is confronting a core weakness of quantum systems: their extreme sensitivity. These delicate instruments are easily disturbed by the slightest environmental noise, from stray magnetic fields to minute temperature shifts. The company's solution is something they call quantum firmware, a layer of intelligent software that acts like a shock absorber for the quantum world. It constantly monitors the sensor and applies corrective signals, protecting the fragile quantum states from the chaos of the real world and allowing them to function reliably outside a perfect laboratory vacuum. This kind of innovation is what makes the commercial sector so vital. Across the globe in the United States, companies like OSense and Inflection are performing their own brand of magic, shrinking massive laboratory setups into compact, robust devices. They are building atomic sensors so small and efficient they could be integrated into a satellite or a submarine, providing precise navigation without any external signals. The agility of these smaller teams is their greatest asset. They can rapidly prototype a new design, test it, fail, and iterate again in the time it might take a large bureaucracy to approve a single meeting. This relentless pace is crucial for a simple reason. It drives down costs and transforms quantum navigation from an expensive laboratory curiosity into a product that can be bought and sold. Venture capital firms are taking notice, pouring billions into this sector because they see its transformative potential extending far beyond space. The same quantum sensors that guide a spacecraft could one day navigate autonomous cars through a tunnel where GPS fails, or pilot robotic submarines in the lightless depths of the ocean. This influx of private money and talent adds a complex, unpredictable layer to the global contest. It means the next world-changing breakthrough might not emerge from a national lab, but from a small, driven team of engineers working in a strip mall anywhere on Earth. This fragile quantum link, the very heart of the system, faces a constant assault in the void, preserving the entangled state of particles, a condition known as quantum coherence, is a battle against the universe itself. Out in space, cosmic radiation, savage temperature swings, and the subtle vibrations of a spacecraft all conspire to disrupt this delicate balance. When this happens, a process called decoherence, the magical connection between the particles, simply snaps. It is as if our two perfectly synchronized clocks are suddenly struck by a hammer, their ticks falling into chaos and the entire navigation system failing in an instant. This is the single greatest technical obstacle standing between a brilliant laboratory demonstration and a reliable tool for guiding satellites and astronauts. To win this battle, engineers are building fortresses at the atomic scale. They wrap the sensitive quantum components in layers of sophisticated shielding, creating a sanctuary against stray magnetic fields and destructive radiation. But shielding alone is not enough. They have developed a form of quantum armor, advanced error correction codes that act like a spell checker for reality itself. These codes can detect when a quantum state is beginning to wobble and apply a corrective nudge, restoring the information before it is lost forever. The most advanced systems go even further, employing active stabilization that constantly monitors the particles, like a musician endlessly tuning a violin to withstand a hurricane. Some researchers are taking a different path entirely, searching for specific types of atoms with states that are naturally more resilient, particles that are simply tougher and less easily disturbed by the chaos of their surroundings. This monumental effort is a fusion of many disciplines, demanding a deep mastery of material science to build the perfect container, quantum optics to manipulate particles with laser light, and control theory to orchestrate it all. The race to build a quantum navigation system is, in its most critical moment, a race to protect a whisper from a storm. But before these delicate quantum systems can ever hope to survive the brutal environment of space, they must first prove themselves in the relative safety of Earth. Deep underground, in laboratories shielded from the city's rumble and isolated from the slightest vibration, scientists are building the prototypes for our future navigation networks. These are not sleek satellites, but complex tabletop setups of lasers, crystals, and kilometers of coiled fiber optic cable, all dedicated to a single task, simulating the immense distances and inevitable interference of a space-based link. Here, researchers create pairs of entangled photons, those mysterious linked particles, and immediately send one of the pair on a long, difficult journey through the winding fiber. This dark, confined pathway perfectly mimics the signal loss and disruptive noise that would corrupt a quantum signal traveling hundreds of miles from orbit down to the surface of the planet. Every failed connection, every lost photon in these experiments is not a disaster, it is a precious lesson. The teams learn how to amplify the incredibly faint quantum signals without destroying their delicate properties. They master the art of clock synchronization with a level of precision that borders on the absurd, aligning timekeeping devices to within a fraction of a nanosecond. And they engineer receivers so incredibly sensitive they can detect the arrival of a single particle of light, a task like trying to hear a pin drop in a hurricane. These terrestrial trials are the ultimate sandbox, a place where theories meet the messy, unforgiving real world. Failure here is a gift, a chance to learn and adapt without the catastrophic cost of a rocket explosion or a dead satellite. The data gathered in these quiet, subterranean labs provides the concrete foundation of confidence needed to justify the immense risk and expense of taking the next great leap, building the unshakable proof that this quantum dream can be made into a working reality. Building this quantum web requires an entire fleet in the sky, not a solitary sentinel. A functional global navigation system will be a constellation of interconnected quantum nodes, each one a sophisticated workshop for creating and sharing entangled particles. This orbital architecture forces a fundamental choice. Do you place the satellites closer to Earth in what is known as low Earth orbit to reduce the time it takes for signals to travel and to make launches cheaper? Or do you position them much higher up where fewer satellites can see more of the planet at once, offering broader coverage from a more stable position? This single decision ripples through every other aspect of the design. To provide seamless, continuous coverage for the entire world, you need enough of these quantum nodes in the sky so that at least one is always in view from any point on the ground or in space. This number could range from dozens to hundreds depending on their altitude and capability. Each satellite in this network becomes a central hub of quantum activity. It must generate pairs of entangled photons, hold them safely in a special device called a quantum memory, and then fire them with pinpoint accuracy across thousands of miles of empty space to another satellite or a user below. The optical systems required for this are unlike any used in conventional satellites. They are incredibly precise lasers and telescopes, capable of aiming a beam of single photons at a target moving at thousands of miles per hour. This is the grand systems engineering puzzle at the heart of the race. It is a three-dimensional balancing act of cost, resilience, and sheer performance. How do you build a network that is robust enough to survive the loss of several satellites, affordable enough to actually launch, and powerful enough to deliver on the quantum promise? Every competing nation and consortium is now working furiously on their own unique answer, sketching their own distinct blueprint for the nervous system of the next space age. The relentless pursuit of a perfect clock defines this entire endeavor. At the very center of every quantum navigation system beats a timekeeper of almost incomprehensible accuracy, a device known as an optical lattice clock. Imagine trapping thousands of strontium atoms in a perfect grid of laser light, holding them so still and isolated that their natural vibrations can be counted with flawless regularity. These clocks are not just precise, they are stable to a degree that defies human experience. One of these devices would take longer than the current age of the universe to gain or lose a single second. This is not a minor improvement, it is a leap into an entirely new realm of timekeeping. This phenomenal stability is the non-negotiable foundation for centimeter-level positioning. When your system can measure the travel time of a signal with such breathtaking accuracy, the resulting location data becomes pin-sharp. But here is where the quantum link transforms this from a collection of excellent clocks into a single, unified system. Each satellite in the constellation would carry its own optical lattice clock, and these master timepieces would be continuously synchronized through their entangled particle links. This creates a distributed network of perfect time, a shared heartbeat for the entire orbital fleet. If one clock, through some microscopic flaw or external influence, begins to drift even a minuscule amount from its partners, that error is instantly detectable. Quantum Link provides an immediate, continuous comparison, allowing the system to apply a correction almost in real time. This shared, hyper-accurate timeline is the silent engine of the entire operation. It allows the system to measure the infinitesimal time differences of signal arrivals, the tiny delays that tell a ship or a missile its exact position in the void. Without this synchronized quantum pulse, the most precise clock in the world is just a lonely, brilliant instrument. With it, the entire network breathes as one, creating a stable, unshakable reference frame for everything that relies upon it. This is the promise of an unhackable signal. Think about the GPS signal your phone receives, a faint whisper from space that can be drowned out by a cheap jammer or mimicked by a sophisticated spoofer. For a military drone or a naval vessel, such interference is not just an inconvenience, it is a catastrophic failure that can lead to capture or destruction. A quantum-linked system rewrites these rules of engagement from the ground up. Its security is baked into the very laws of physics, a principle known as the no-cloning theorem. This fundamental rule of quantum mechanics states that it is impossible to create a perfect, undetected copy of an unknown quantum state. Picture a sealed envelope containing your navigation data. With a normal radio signal, an enemy could secretly open the envelope, read the message, and reseal it without you ever knowing. But with a quantum signal, the envelope is made of a magical paper that crumbles into dust the moment anyone tries to peek inside. The act of observing the quantum particles, of measuring them to steal the information, unavoidably alters their delicate state. This disturbance creates errors, a sort of quantum static that the legitimate users on the other end of the link will see immediately. They do not just lose their signal, they receive a bright, flashing warning that someone is listening in. This changes everything. A pilot flying through contested airspace would know instantly if an adversary was trying to feed them false coordinates, allowing them to switch to a backup system or abort the mission before flying into a trap. A cargo ship navigating a narrow strait could trust its charted course without fear of being lured onto rocks by a malicious actor. This is not merely a stronger lock, it is a lock that screams when touched. This quantum advantage transforms navigation from a vulnerable utility into a trusted guardian, creating a foundation of positional truth that the modern world has never known. The profound military implications of this technology cast a long shadow over the entire race. The first nation to deploy a reliable quantum navigation system will secure a decisive and potentially unassailable strategic advantage. Consider the challenge of guiding a hypersonic glide vehicle, a weapon that maneuvers through the upper atmosphere at speeds exceeding Mach 5. Its incredible velocity means even a momentary lapse in positioning, a single misstep from a jammed signal, could send it hundreds of miles off course, missing its target entirely. A quantum-linked system provides the continuous, spoof-proof guidance such a weapon demands, turning a theoretical threat into a precise and unstoppable one. Beneath the waves, the stealth of a submarine is its greatest defense. Today, these vessels must periodically rise closer to the surface to get a clear GPS signal, a dangerous moment that reveals their position. With a self-contained quantum inertial navigation system, a sub could chart its course through the lightless depths for months, never needing to break its silent vigil. This same principle enables swarms of autonomous drones to operate in perfect concert within environments deliberately stripped of GPS, such as a contested urban canyon or an enemy electronic warfare bubble. They would not be blind, but would instead navigate by their own shared quantum sense of time and space. This capability is the cornerstone of a new military doctrine known as all-domain operations, the seamless integration of forces across land, sea, air, space, and cyberspace. Quantum navigation provides the unshakable, common operational picture that makes such integration possible. It ensures that every soldier, every pilot, and every ship captain is looking at the same flawless map, synchronized to the same perfect clock. This is why the quest is treated with such urgency behind closed doors. It is not merely a scientific ambition, it is a direct and powerful contributor to both national defense and offensive power, a top priority asset that could redefine the global balance of power for decades to come. The military may be driving this quantum revolution, but the civilian world stands to gain just as much, perhaps even more. The same technology designed to guide a missile will soon be steering the cargo ships that carry our goods across the oceans. Picture an autonomous freighter, a colossal vessel with no crew on the bridge, navigating a narrow strait in a thick fog. Its quantum sensor feels every subtle shift in the ship's momentum, building a perfect internal map of its journey without ever needing a signal from the shore. This is not science fiction. It is the inevitable next step in global logistics, promising to make shipping safer, cheaper, and infinitely more reliable. On our city streets, the persistent problem of the urban canyon, where tall buildings block and reflect GPS signals, would simply vanish. Your future driverless car would not be confused by a tunnel or a dense downtown. It would know its exact lane position to within centimeters, guided by a chip-sized quantum accelerometer that feels every turn and every change in speed, creating a seamless and unbreakable chain of positional awareness from highway to underground garage. The skies, too, would become far more efficient. Quantum navigation would allow aircraft to fly more direct routes, saving fuel and reducing flight times, while enabling perfectly spaced landings in zero visibility. But the most profound commercial transformation will happen far above us in the growing space economy. Around the moon, a bustling traffic of supply landers, tourist vehicles, and construction drones will need a shared, ultra-precise navigation system to avoid catastrophic collisions. Quantum-linked satellites would provide that common, unjammable reference frame, allowing two spacecraft to perform an autonomous docking maneuver with the gentle precision of a handshake, entirely without human intervention. This same technology would supercharge our view of Earth itself. Satellites equipped with quantum gravimeters could map underground water reservoirs by detecting minute changes in the planet's gravitational pull, or track the slow, massive movement of magma deep beneath a volcano. They could measure the alarming loss of ice mass from the polar ice sheets with unprecedented accuracy, giving us the clearest possible picture of our changing climate. The economic potential here is not just an improvement, it is a fundamental rewrite. We are looking at the birth of entirely new industries built on a foundation of perfect location data, making our world safer, more connected, and more intelligently managed than ever before. A critical question now looms over this entire technological race, one of power and protocol. Who gets to make the rules for this new quantum frontier? Currently, no international framework exists to govern the use of these quantum signals in space. We are staring at a potential orbital Wild West, where competing systems could clash in the silence above us. The most immediate problem is spectrum allocation. Quantum links use delicate beams of light, and if two nations aim their quantum signals through the same patch of space, the resulting interference could scramble both systems, leaving everyone blind. Then there is the challenge of interoperability. Will an American spacecraft be able to understand the quantum positioning data from a European satellite in an emergency? Or are we building a new tower of digital Babel in the stars? Perhaps the most profound issue is establishing norms of behavior to prevent a rapid and destabilizing arms race. Without clear rules, one nation's demonstration of a quantum-guided weapon could be seen by another as an act of aggression, triggering a cycle of escalation. Organizations like the International Telecommunication Union and the United Nations Committee on the Peaceful Uses of Outer Space have started these difficult conversations. But the pace is glacial. The sleek engineering of quantum satellites is advancing at a sprint, while the tedious, essential work of diplomacy moves at a crawl. This gap between technological capability and political agreement is a dangerous vacuum. Creating a governance structure that is both fair to all nations and secure enough to prevent chaos is perhaps the most complex political puzzle of our time. The success of this quantum revolution will not be measured in picoseconds alone, but in the strength of the peace it helps to build. The financial engines of this quantum race are roaring to life, with tens of billions of dollars now flowing into the field. This staggering level of investment is the single clearest signal of the transformative power these nations and corporations believe they are chasing. A significant and growing portion of this capital is specifically earmarked for quantum sensing and navigation, a dual stream of funding from public treasuries and private venture funds. For governments, this spending is framed not as an expense, but as a strategic necessity, a non-negotiable investment in future security and sovereignty. In parallel, private investors are placing their bets on a different kind of payoff, the creation of a massive global market for quantum-enabled services. They are not just funding research, they are building the foundation of entire new industries. The ultimate prize here is more than just a functional system. It is the chance to establish a de facto global standard. The first entity to deploy a scalable quantum navigation network could effectively set the rules for everyone else, much like the GPS standard once did. This winner-take-all dynamic promises a torrent of economic rewards, from licensing the core technology to every satellite manufacturer, to selling the specialized hardware, to operating the exclusive data service that guides the world's ships, cars, and aircraft. This potential for immense return has ignited a fierce and global war for talent. The relatively small pool of top quantum physicists and engineers has become the most valuable resource in this contest. These specialists are being offered extraordinary compensation packages, stock options, and state-of-the-art research facilities, as nations and companies compete to lure them away from rivals. But the economic stakes extend far beyond direct profits from the technology itself. A nation's success or failure in this arena will profoundly influence its standing in the high-tech supply chains of the 21st century. The ability to produce the advanced lasers, ultra-pure crystals, and fault-tolerant components for quantum systems will become a marker of technological leadership, creating high-value jobs and securing a country's role not just as a consumer of advanced technology, but as its primary architect. This financial landscape reveals the true scale of the ambition, transforming a scientific pursuit into a high-stakes contest that will reshape the global economic order. This silent, self-contained form of navigation is the ultimate goal. Quantum inertial navigation systems, or QINs, offer a path to achieve it, representing a radical departure from anything that came before. Unlike systems that must constantly check in with satellites, an inertial navigation system is entirely self-reliant. It works by continuously measuring every single acceleration and every rotation from a known starting point, building up a perfect internal log of its entire journey. Think of it as the most sophisticated dead reckoning imaginable. You close your eyes at your front door, and by meticulously counting every step you take and every turn you make, you can still point to your exact location hours later. The problem with traditional inertial sensors is that they are imperfect. Tiny, microscopic errors in measuring those movements slowly accumulate. Over time, this drift adds up, and your perfect internal map begins to blur, leaving you lost. This is where quantum physics performs its magic. Quantum sensors, built on the principles of atom interferometry, are designed to be nearly immune to this drift. The heart of such a sensor is a cloud of atoms, chilled to a fraction of a degree above absolute zero. At this profound cold, the atoms behave not like tiny balls but like spreading waves. These delicate quantum wave functions are exquisitely sensitive to the universe. Any movement, any acceleration or rotation of the sensor directly changes the phase and pattern of these atomic waves. By shining lasers on these cold atoms and observing how these quantum wave patterns shift, the sensor can deduce its own motion with staggering precision, without ever asking the outside world for confirmation. The implications are breathtaking. A submarine equipped with a QINS could traverse the ocean depths for months, charting a course through lightless trenches with such minimal error that it would surface within meters of its intended location. A spacecraft on a years-long journey to Mars could course correct with absolute confidence, its position known not by a faint whisper from Earth, but by the immutable laws of quantum mechanics playing out inside its own hull. This is the Holy Grail, a technology that severs the last fragile tether to external signals and grants true navigational freedom. It is a capability that promises to unlock the darkest corners of our world and the deepest reaches of our solar system. That quantum link must survive a journey far more perilous than the vacuum of space. It has to plunge through our own turbulent atmosphere, establishing a reliable connection between a satellite screaming through orbit at thousands of miles per hour and a fixed ground station is a monumental test of precision. The satellite must aim its delicate quantum transmitter, a device designed to emit single photons, at a receiver on the ground that may be no larger than a dinner plate. And it must hold that aim perfectly steady. The first great enemy is the air itself. Our atmosphere is not a calm window, but a seething, turbulent fluid. It bends and distorts light, causing the tiny stellar twinkle we see at night, a beautiful effect that would utterly destroy a fragile quantum signal. To fight this, engineers deploy systems called adaptive optics. Picture a mirror that can change its shape hundreds of times per second. This system fires a bright guide star laser into the atmosphere, measures how the returning light is scrambled, and then commands the mirror to warp itself in the exact opposite way. It pre-corrects the outgoing quantum signal, cancelling out the atmospheric distortion before it even happens, carving a clear pathway for the photons. Then there is the problem of shear motion. The satellite's immense velocity creates a Doppler shift, stretching the wavelength of the light, much like the changing pitch of a passing siren. The ground station must constantly retune its receiver to catch this shifting signal, and all the while clouds threaten to block the path entirely, and the vast majority of photons are absorbed or scattered into nothingness by molecules in the air. This is why these systems are built to operate on the very edge of what is possible, relying on detectors so sensitive they can register the arrival of a single particle of light. The successful demonstrations by satellites like Mishus were not just experiments, they were landmarks of human ingenuity. They proved that we can thread a quantum needle across hundreds of kilometers of chaotic, moving air, a feat that transforms a theoretical possibility into a tangible, working reality. This fragility of the quantum signal over vast distances presents its own unique puzzle. To weave a web that stretches from pole to pole, or even from Earth to the Moon, we cannot rely on a single, impossibly long thread of entanglement. The signal would simply fade into nothingness. The solution lies in a remarkable piece of quantum engineering known as the repeater. This is not a simple amplifier you might find in a classical network. You cannot just copy a quantum state and boost its strength. The fundamental laws of physics forbid it. Instead, a quantum repeater is a form of intelligent intermediary, a trusted broker for entanglement. It works by creating two separate, shorter links of entanglement, one with you and one with your intended partner far away. Then, through a delicate operation called entanglement swapping, it merges these two independent links into one. The repeater effectively ties two short ropes together to make one long one, creating a direct quantum connection between the two endpoints who never directly interacted. This process can be repeated hop by hop to cover any distance imaginable. Building a machine that can perform this quantum handshake reliably in the harsh environment of space is one of the single most important technical hurdles left to clear. A network of these repeaters would act as the vital relay stations for a future quantum internet, the backbone that makes instantaneous, secure communication possible between a research base on Mars and mission control on Earth. They are the key to breaking the cosmic speed limit that currently chains our quantum ambitions to Earth, extending the reach of this new technology across the entire solar system. A new constellation of quantum eyes in the sky brings with it a silent, growing threat. The very orbits we need for this advanced navigation are already clogged with the ghostly remains of past missions, a swirling cloud of shrapnel traveling at 17,000 miles per hour. Each new quantum satellite sent into this environment is a gamble, its delicate optical telescopes and laser arrays uniquely vulnerable. A paint chip from an old rocket stage, no larger than a grain of sand, could strike with the force of a bowling ball, instantly turning a billion-dollar quantum node into just another piece of the debris field it was meant to navigate. This creates a dangerous paradox. To build a resilient navigation system, we must first solve the problem of an increasingly chaotic and dangerous space highway. The risk is not just to the satellites themselves, but to the entire orbital ecosystem. A single catastrophic collision can generate thousands of new fragments, triggering a chain reaction known as the Kessler syndrome, where the density of debris becomes so high that certain orbits are effectively closed off for generations. The promise of a quantum future could be shattered before it even begins, lost in a self-made storm of metal and silicon. This forces a profound shift in design philosophy. The next generation of satellites cannot simply be launched. They must be built with their entire life cycle in mind. Engineers are now prioritizing designs that include robust propulsion for end-of-life maneuvers, ensuring these vital assets can be guided into a safe graveyard orbit or a fiery atmospheric disposal. The concept of sustainability is being redefined, extending from the ground all the way to geostationary space. The environmental consideration does not stop at the edge of the atmosphere. The production of these sophisticated quantum components demands immense energy and rare earth minerals, while the sheer number of rocket launches required for a full constellation carries its own carbon footprint. The space industry finds itself at a crossroads, tasked with building the most advanced technology humanity has ever conceived while also becoming a leader in green engineering. This means pioneering new, less polluting rocket fuels, adopting circular manufacturing processes that minimize waste, and actively participating in the urgent mission of debris removal. Several startups are already testing technologies like harpoons, nets, and magnetic tow lines to capture and deorbit defunct satellites. The ultimate success of our quantum ambitions will be measured not only in picoseconds of accuracy, but in our willingness to clean up after ourselves, proving that we can reach for the stars without littering the path for those who follow. So when will this quantum future truly arrive? The path from laboratory breakthrough to an operational constellation is a carefully mapped, though fiercely competitive marathon. Right now, we are in the critical phase of advanced research and ground demonstration, where every successful experiment moves the entire field one step closer to reality. The next 5 to 10 years will be defined by a new wave of dedicated technology demonstrators in space. These are not full systems, but essential proof of concept missions. We will see satellites launched with the specific job of testing a single, vital component, like a quantum memory unit that must hold its entangled state for days, or an optical lattice clock proving its long-term stability against the brutal reality of radiation. Success in these focused missions builds the confidence needed for the next, more complex leap. Based on this phased approach, a small-scale, operational system for specialized military or government use could become a reality within the next decade. This initial deployment would likely serve a select group of high-priority users, such as guiding hypersonic vehicles or providing a secure navigation backup for nuclear command authorities. It is the prototype for ultimate power. For the rest of us, the vision of a full global constellation guiding our cars and phones is further on the horizon, probably 15 to 20 years away. This widespread civilian rollout is contingent on conquering the twin giants of technical feasibility and staggering financial cost. The current timeline is a projection, not a promise. A single, stunning breakthrough in a stubborn area like quantum error correction could slash years off the schedule, sending progress into overdrive. Conversely, a shift in political priorities or a global economic downturn could freeze funding and introduce painful delays. The race is on, and while the finish line is not yet in sight, the sound of sprinting footsteps is growing louder every day. This competition for quantum dominance feels chillingly familiar to historians. We are witnessing the early stages of a quantum Cold War, a silent, high-stakes struggle not for nuclear bombs but for absolute information superiority. The prize is no longer just a bigger weapon, but the very fabric of perception and truth in the digital age. This new arms race is carving the world into two distinct technological spheres, one led by the United States and its allies, and another centered on China and its partners. Each bloc is now pouring its resources into developing its own quantum navigation systems, its own security protocols, and its own technical standards. The inevitable outcome of this parallel development is a fractured global reality. Imagine a world where your autonomous car, built in America, cannot read the quantum signals from a Chinese satellite, or where a European cargo ship becomes lost in a port that operates on a different quantum standard. This is the emerging threat of a splinternet for navigation, where the seamless, interconnected world we take for granted is shattered into incompatible digital islands. The danger extends far beyond mere inconvenience. This technological bifurcation fuels a vicious cycle of mistrust. Every satellite launch by one side is seen by the other as a potential military asset, a move in a grand strategic game. Every advance in quantum sensing is interpreted not just as scientific progress, but as a step towards a new form of warfare. Without clear communication and established rules, this environment is a tinderbox. A simple software glitch in one nation's quantum system could be misread by an adversary as a deliberate act of jamming or spoofing, escalating tensions in moments. The great challenge for global leaders today is to navigate this narrow path. They must encourage the fierce competition that drives humanity's greatest innovations, while simultaneously building strong guardrails to prevent this new frontier from descending into a chaotic theater of conflict. The question is no longer just who will win the race, but whether we can agree on the rules of the road before the finish line is crossed. This extraordinary power to pinpoint any object on the globe demands a conversation about responsibility. With such a precise and powerful global utility now within our grasp, we must ask ourselves a difficult question: who gets to hold the reins? The same quantum sensor that guides a rescue ship through a hurricane could, in the wrong hands, become the most sophisticated tracking device ever conceived. It could follow a single individual's movements with centimeter-level accuracy, from a city street down to a specific room in a building, creating the potential for a surveillance state with capabilities we have only ever imagined in fiction. This is the inherent tension of dual-use technology, a term that sounds academic but carries immense weight. Every peaceful breakthrough in quantum navigation, every advance meant for mapping asteroids or navigating deep-sea research vessels, can be rapidly refashioned. The same principles that allow for autonomous ship convoys could guide swarms of lethal drones. The core physics does not distinguish between a humanitarian mission and a military strike. This creates a fundamental ethical race, one that runs parallel to the technological one, and it is a race we cannot afford to lose. There is another, more subtle division looming. The staggering cost of developing and launching these quantum constellations risks creating a new kind of global inequality. Will access to this unhackable, ultra-precise navigation be a universal right, or will it become a luxury service, available only to the wealthiest nations and the most powerful corporations? We could see a world split into navigational haves and have-nots, where one group of ships sails with perfect certainty, while another remains vulnerable to spoofing and jamming. This is not a future we should accept by default. This is why the voices of philosophers, ethicists, and the public are not a secondary concern. They are as vital as the engineers and physicists. We need to build the ethical frameworks alongside the quantum hardware, establishing clear red lines and shared principles before the technology is fully operational. The goal must be to steer this incredible power toward global security and shared prosperity, ensuring that the quantum compass we build for humanity points not toward control, but toward a future that benefits everyone. This vast stream of perfect data demands a mind powerful enough to understand it. The sheer volume of information flowing from a quantum constellation would overwhelm any human team, a torrent of measurements so precise and continuous it would be meaningless noise without an intelligent interpreter. This is where artificial intelligence enters the stage, not as a separate tool, but as the essential brain of the entire operation. These sophisticated algorithms will manage the intricate orbital dance of the satellites themselves, constantly calculating which spacecraft should link with which others to maintain the quantum web, all while conserving precious power and avoiding potential collisions. They will act as the system's tireless physicians, running continuous diagnostics to spot a failing component or a subtle drift in a clock long before it becomes a critical failure. But the role of artificial intelligence goes far beyond simple management. The quantum signals themselves, for all their perfection, are still subject to the universe's chaos. Machine learning systems will be trained to recognize the subtle fingerprints of interference, whether from solar radiation or the residual tremors of a satellite's own machinery. They will learn to filter out this noise in real time, cleansing the signal and guaranteeing the fidelity of the final navigation solution. Think of it as a master restorer working on a priceless painting, carefully removing the grime of centuries to reveal the perfect image beneath. These intelligent systems will also learn to predict the environment itself. They will model the shifting density of the upper atmosphere to anticipate how it might bend a laser beam, or calculate the local gravitational pull over a mountain range to correct its tiny influence on a quantum accelerometer. This creates a powerful, self-improving loop. The quantum sensors provide a fire hose of flawless, ground truth data, and the artificial intelligence drinks it in, learning and adapting to make the entire system smarter, faster, and more resilient with every passing second. This fusion is the final, critical step. It is what transforms a collection of brilliant quantum instruments into a trusted, living utility, a service that can reliably guide a pilot through a storm or a rover across the dusty plains of Mars. Our journey to the stars is currently held back by a simple, frustrating delay. When a rover on Mars sends a signal to Earth, it takes between 4 and 24 minutes for that message to travel one way. Navigating a spacecraft with that kind of lag is like trying to park a car by only looking in the rearview mirror. A quantum-linked navigation system shatters this limitation, creating an active, living map of the inner solar system. The foundation of this map would be a network of quantum nodes positioned at stable gravitational waypoints known as Lagrange points. These are places in space where the pull of Earth and the Sun balance out, allowing a satellite to hold its position with minimal effort. From these silent orbital outposts and from satellites circling Mars or other worlds, a continuous web of quantum links would be woven. A ship on its way to Jupiter would no longer be a lonely traveler guessing its path. It would instead be an active participant in a celestial conversation, constantly checking its position against the quantum clocks on a node near Earth and another already in orbit around Mars. It would perform a form of interstellar triangulation, not with slow radio waves, but with instantaneous quantum comparisons. This is the difference between following a hand-drawn map and watching your position update in real time on a flawless digital globe. This self-reliant precision is the single most important requirement for the next phase of exploration. It turns a perilous, months-long leap into a predictable, managed voyage. Imagine automated cargo landers approaching a Martian settlement, executing a perfect, gentle touchdown without a single instruction from mission control millions of miles away. Picture a crewed vehicle navigating the complex gravitational field of the Jovian system, its computer confidently threading a path between moons because it knows its exact location down to the meter. This autonomous capability dramatically reduces the risk of mission failure, making the outer planets accessible not just to rugged, one-off probes, but to a sustained fleet of robotic explorers and eventually human pioneers. Building this quantum highway is not an optional upgrade. It is the fundamental infrastructure we must construct to evolve from a species that occasionally visits space to one that truly lives there. This race is ultimately a story about us, about what humanity chooses to build when the known limits of physics begin to fade. We have ventured from the spooky connection of entangled particles to the high-stakes strategies of global superpowers, all chasing a future defined by unshakable truth in position and time. The promise is a world where our essential systems are secure, where our ships and cars navigate with flawless certainty, and where our path to the stars is no longer a dangerous leap but a managed highway. The financial and strategic stakes are almost beyond comprehension, involving trillions of dollars and a fundamental reordering of global influence. Yet, for all the fierce competition, there is a profound shared triumph here. We are collectively bending the strangest rules of the universe to our will, turning abstract equations into the bedrock of a new reality. As this acceleration continues, it places a dual burden upon our shoulders. We must innovate with relentless speed, but we must also govern with foresight and wisdom. The destination is a cosmos made accessible, a future where humanity moves through the void with a confidence we once only attributed to science fiction. This is not the end of the journey. It is the very beginning of a new chapter in our story, one whose course we are setting right now for all the generations that will